In this example, we're being asked to compute the member forces in the truss. So as part of the given information, let's go ahead and draw this truss together. I have a truss geometry that looks something like this. Remember, each one of these intersection points is represents the a joint on the truss. Okay, so we're going to have joint A, joint B, joint C, joint D, joint E, F, and G. And we're going to go ahead and put dimension lines here. This is going to be 12 feet. It's going to be 10 feet, 10 feet, and 8 feet. Okay, and let's go ahead and put our applied loads here. We're going to have a vertical load at B of 500 pounds, and then we're going to have, let me move E, we're going to have a horizontal load at E of 700 pounds. Okay, so this is our truss. We have all the dimension lines we need, and we're ready to get going on this. So the first thing we need to look at is we need to ask ourselves, can we solve for external support reactions, and do we have to? All right, so remember, when you're doing method of joints, you always start at a joint where you have at least one known force, but at most two unknown forces. So if you look at our problem here, we have two joints where we have something we know. We have joint B with 500 pounds. We have joint E with 700 pounds. But if you look at both of these joints, how many unknowns do we have? Well, we have way too many unknowns, right? We have let's see, 1, 2, 3, 4, 5 unknowns at joint B right now, and 4 unknowns at joint E right now. So so you have to again, you can't start there. You have to start at a point or at a joint where you at most have 2 unknowns. Now, we also know from our knowledge of zero force members that we may be able to recognize some here. So by one of our zero force member criteria, can you see on here where we have some zero force members? So I would say you can notice that BF is a zero force member. All right, notice that if you look at joint F right here, you have no applied loads, no external reactions, and you have 2 collinear members, so the third member is a zero force member. And by the same reasoning, CE is also a zero force member, looking down at joint C right here. Okay, so that can make our lives a little bit easier. So in order to get the method of joints process going, we still have to solve for external reactions. So we're going to state that here. In order to begin method of joints, we must solve for external support reactions first. Okay, there's no way we can start anywhere else for this particular problem. So here's what I'm going to do. In order to save a little bit of time in this video, I'm just going to kind of sketch on here my external support reactions on the original figure instead of redrawing the entire figure with a new free body diagram. In your homework, I do want you to do that, but again, to keep this video with a manageable time, we're going to just do it this way. So we have AY and we have an AX here. And then over here we have a DY. And there we go. Those are our three unknowns. So now what we can do is solve for some of these unknowns. Here's what I'm going to do. I'm going to say sum of the moments about point A equals 0. And I'm going to say counterclockwise is positive. And I'm going to solve for DY in this step. So when we do that, we're going to have DY times 28 feet, right? That's its moment arm right here. And then look at what else we have causing a rotation about point A. We have the 500 pounds at point B, so that would be oh man, what is that? Clicked on the highlighter, whoopsie. We would have minus 500 pounds times 10 feet. And then we also have the 700 pounds causing a rotation about point A. So we would say minus 700 pounds times 12 feet equals 0. And AX and AY do not come into play here because we are taking the moment about point A. So do a little bit of rearranging. We can solve for DY directly, and let's see what we get. We should get 500 times 10, and then we say plus 700 times 12, and then we divide that by 28, and we should get 478.6 pounds. It is positive, so it's reacting upwards. Then we can say sum of the forces in the y direction equals 0. And so everything in the y direction we include in this equation. So AY minus 500 pounds plus 478.6 pounds equals 0. So we get a value of AY equals 21.43 pounds, and it is positive, so it's reacting upwards. And then hopefully you can clearly see just by looking at it, what is AX? Well, the only force in the overall truss that you have in the X direction is 700 pounds. So AX should be 700 pounds pointing to the left, but we can write that out. Sum of the forces of the X direction equals 0. So we say AX plus 700 pounds equals 0, and we'll get AX equals 700 pounds is negative, which means it's 700 pounds pointing to the left. It's pointing in the opposite direction here that we assumed, right? Remember, whenever you solve for external support reactions, if you get a value that's pointing in the opposite direction of what you assumed, then, if you get a value that's negative, it's pointing in the opposite direction of what you assumed, all right? So that should not be anything new to you. So now we're ready to go. Where should we start? We have the external reactions. Where should we start now? Well, could we start at point A? Yeah, absolutely. Now that you know AX and AY, the only two unknowns you have are AG and AB. So sure, you could start at A. You could also start at D, right? You know DY, and the two unknowns would be DE and CD. So you could start at either one of these joints. I prefer to pick a joint to start at and just move to the opposite end of the truss. So how about we just start at A and we perform our calculations and we move to towards the right side of the truss, okay? I don't think it's a good idea to kind of like hop around from joint to joint and not go in order. That's a good way to confuse yourselves. So I'm gonna make a comment here. I'm gonna say let's start at A and move towards D. Okay, so I'm gonna start by saying let's look at a free body diagram of joint A. So at joint A, what did we have here? We had 21.43 pounds going up, and then we had 700 pounds pointing to the left. Here's joint A, and then look at these forces we have here. We have an AG and we have an AB. Now, what direction are those pointing? Well, remember, when the practice is point unknown forces away from the joint. That's going to assume tension. So we're going to have F sub AG here, and then we're going to have F sub AB here. And that's a pretty simplistic looking scenario. And hopefully we can just look at this and we can say by sum of the forces in the x direction equaling 0, we'll have negative 700 pounds plus FAB equals 0. FAB equals 700 pounds. It is pointing, it comes out positive, so it is in fact pointing to the right, which means it is in fact in tension. So then we're going to say sum of the forces in the y direction equals 0, and we're going to have FAG plus 21.43 pounds equals 0. FAG equals negative 21.43 pounds. And when you get a negative value here, what does that mean? Well, it means FAG is actually pointing in the opposite direction of what we assumed, which in this case would be compression. So we're going to say F sub AG equals 21.43 pounds in compression, okay? And what I like to do is I like to just put a little check mark on the members when I'm done with them, okay? So where can we go next? Can we move to joint B next? Well, let's think about it. We know we have 500 pounds hanging there, and we now also know what the force in AB is. And we know that, BF is 0. But how many unknowns do we have at joint B at this time? Well, right now, we still don't know the force in BG or BE or BC. So we can't go to joint B next. We still have too many unknowns. We have 3 unknowns. What about joint G? Sure, that would work. We know AG now. We just calculated that, and that means the only 2 unknowns we have are G, F, and BG right here. So I'm going to say, let's look at a free body diagram of joint G, okay? And so when we have joint G, we have an unknown, let me color coordinate. We're going to have an unknown force here, an unknown force here. And remember, we know the force in AG right now, right? It's this right here, and it's 21.43 pounds, okay? So that's kind of what we have now. Now, we also need to get some information about this angle. We don't have it directly, but can we get it? Yeah, absolutely. We can use the fact that we have these dimension lines here. We could take an arc tangent if we want. We got a couple of options. So if you notice, we have, let's see, 12 and 100. So that's not really a very nice slope ratio, is it? I would just say, let's go ahead and get, let's call this angle maybe theta right here. And we would say theta is arctangent of 12 feet over 10 feet. So here's theta. Theta is arctan 12 feet over 10 feet. You could have done this at the beginning of the problem, by the way. You could have gotten all these interior angles from the get-go. So I get 50.19 degrees as that theta angle. And again, we have F, the force in FG, and the force in BF. Force in FG, force in BF. And I prefer to label these subscripts in alphabetical order. That's why I say FG and BF, by the way, in case you were wondering. Now, my next question, before we actually calculate anything, why is this 21.43 pounds pointing up when we're at joint G? Well, remember, we calculated the force in FG as 21.43 pounds in compression. So when we were at the free body diagram of A, the force in AG is actually pointing down towards A, which means on the opposite side of that member, when we're at joint G, it's pointing still at joint G. It's got to be pointing equal and opposite. So make sure you understand that directionality. All right, so what do we do next? We're going to say sum of the forces in the y direction equals 0. And when we're here, we're going to say 21.43 pounds minus FBF times the sine of 50.19 degrees equals 0. FBF equals, and let's see what we get. I'm punching this in my calculator right along with you. 21.43 divided by sine of 50.19, and you should get a force of you should get 27.90 pounds in tension. And then we're going to say sum of the forces in the x direction equals 0. And when we do that, we're going to say FBF times the cosine of 50.19 degrees plus FFG equals 0. And, we know FBF, right? We just calculated it, so we can get FFG directly, FFG, and it will be a negative value. So let's multiply this by cosine 50.19, and I get 17.86 pounds, which, because it came out negative, and again, we were assuming FFG is in tension, it's going to be 17.86 pounds in compression. So we can go ahead and check these two member forces off. Okay, where can we go next? Well, now you have a couple of options. You could go to joint B, because now we have enough information where we can go to joint B, right? We know AB, BG, and we know that BF is a zero force member. So we could end up going to BE right now and BC, getting these two unknowns. Or we could just go to joint F right now. I'm going to say let's go to joint F. We only have the one unknown, and that's going to be pretty straightforward to get. So, but again, you do have options here. There's not necessarily one way of doing this. FBD, joint F, and we know that this was a zero force member that was vertical here, and we got FFG as 17.86 pounds, and that was in compression. Remember, we calculated it. It was negative, so in free body diagram G, it's actually pointing at G, which means that on the opposite side of the member, when you're over at F, it's pointing at F, so indicating compression. And we have this unknown force. What was this labeled again? I have to scroll back and remind myself. FEF, okay? FEF. Now, this one should be pretty straightforward. If you sum forces in the x direction equaling 0, hopefully you can clearly say that FEF is equal to 17.86 pounds, also in compression. If you can't see that, show another step of calculation, but it is the same magnitude, and it's pointing at the joint right there. Again, that joint must be in equilibrium, so equal and opposite forces. So I'm going to check this off now. All right, where can we go next? Like I said, you got some options. We could go down to joint B if you wanted. We only have two unknowns that we could solve for, or we could go to joint E right now, okay? We could go to joint E and get BE and DE, all right? I'm just going to say let's go to joint B now, okay? But again, if you wanted to, you could go to joint E, no problem, all right? So let's go to joint B just because I want to. So FBD of joint B. And at joint B, remember we had the 500 pounds here. And what else do we know? There's a lot going on at B. We had a zero force member vertically here. We have FAB and FBG. So let's populate this. Here's that zero force member. What was FAB? That was from an earlier calculation. We got to look around for it. 700 pounds in tension. Okay, so that's going to be pointing away from the joint. And then what was FBG? I believe that's what it was, right? F. I said check myself. FBG. Where is our FBG? We should have gotten that. Let's see, FFG, FBG. Did I label something wrong? It looks like I labeled something wrong here. FAG. Yeah, it looks like I labeled something wrong here. The calculation should be right, but yeah, this, look at this. This should be FBG. So let's fix that. FBG. Yep. FBG. So FBG is right here. FBG. FBG. That's just a labeling issue. Make sure I didn't label anything else wrong. Yeah, I just labeled that wrong. We're good. So, so what was FBG? 27.9 pounds in tension. So that's going to be right here, 27.9 pounds. And then what other unknowns do we have here? We've got FBE and FBC. FBE and FBC. Now, what is this angle here? Well, it turns out this angle is the same angle theta of 50.19 degrees. And again, this is also theta right here. So you can, perform an arctangent calculation to verify that, but it is the same angle. So let's go ahead and do these calculations. Now, again, there's a lot more going on here, so we just got to be careful. I'm going to say sum of the forces in the x direction equals 0, and we're going to say negative 700 pounds. Then we're going to say minus 27.9 pounds times the cosine of 50.19 degrees. And then we're going to say plus FBE times the cosine of 50.19 degrees. And then plus FBC equals 0. All right. And then we're going to say sum of the forces in the y direction equals 0. And we're going to have 27.9 pounds times the sine of 50.19 degrees plus FBE times the sine of 50.19 degrees minus 500 pounds equals 0. And here we can solve for FBE directly. That's our only unknown in the y direction. So FBE is going to equal the following. We're going to have 500 minus 27.9 times the sine of 50.19. And then we're going to say divided by sine of 50.19. And so I get FBE equals 623 pounds in tension, okay? And then we can substitute FBE into our X equilibrium equation and get FBC. So let's see what we get for FBC now. We're going to take FBE times cosine 50.19, and then minus 700 minus 27.9 times the cosine 50.19. Yep, and I get 319 pounds in tension. Watch your signs when you rearrange things. So I can go ahead and put a little check mark by each of those member forces here. Check, check. And I'm almost done now. I can go to joint C and get the force in CD, and then I can go to joint D and get the force in DE. So let's go ahead and do that real quick. We're going to say free body diagram of C, and at C, I think we had a zero force member here. We have the force in CD here, and then we had, what was the force in BC? We just calculated that, I think. 319 pounds. So hopefully clearly you can see that the force in CD equals 319 pounds in tension. Forgot my tension right there. And now we can go to a free body diagram of D. And we have dy here. And we calculated dy earlier at the very beginning, right? That was 478.6 pounds. So write that here, 478.6 pounds. And we have FCD is 319 pounds in tension. And then our last unknown was right here. This is the force in, I believe, DE. Let's make sure I didn't mislabel something. Yep, DE. Now, I need this interior angle, right? That is not the same as theta. If you notice, this bay is defined by different dimensions, okay? So in this bay, I'm going to call this maybe phi, and we can calculate phi as the arctangent of 12/8. So again, that is a different angle than theta. So we'll call this phi, give it a different name. Arctangent of 12 feet over 8 feet. And let's see what we get. I get 56.31 degrees. And then I'm going to say sum of the forces in the y direction equals 0. You could use sum of the forces in the x direction equals 0 too. It doesn't matter. Either one of these equilibrium equations at this point will get you FDE because you just have one unknown. So we would say FDE times the sine of 56.31 degrees plus 478.6 pounds equals 0. And so FDE will end up equaling 478.6 divided by sine 56.31, and I get a negative 575.21 pounds, which is 575.21 pounds in compression, okay? Now, if you want to just double check yourself real quick, you could check yourself by saying sum of the forces in the x direction equals 0, and make sure that you get the same value of FDE that you just got when you sum forces in the y direction. So I'm not going to write that, but I'm going to punch that in my calculator. I'm going to say 319 divided by cosine of 56.31. And I get the same thing, 575 pounds, plus and minus a couple decimal places for round off. So at this point, you want to make a summary, and I want you to list member forces in this summary. All right.